starts at a very specific point here that the curve begins. And then they go up to a certain distance where they reach their max velocity. And then from that point on, they either keep that same velocity or they slow down. So it has it that it gets down to 35 kilometers per hour at the finish line, but all we really care about is that after this point, it is less than 40 kilometers per hour. And there's a lot of other type of information in the problem statement that talks about, so they run 60 meters, and then they go 70 meters, and then they go to the finish line, and the whole thing's 200 feet, and all this other nonsense. But if you hone in on what you're actually looking for, you can shuffle around and deal with all of the excessive variables that they're given. When it asks for AX, A max, what you're looking for is the max change in speed, so that would be A tangential, and then you're also looking for the max acceleration of the change in direction, which is A normal. And we'll get to those a little bit more in detail, but the maximum is going to be the point where both of those are max. And at that point, you can define the max speed is the max velocity. So when it's looking for the very specific point, you can define your V final as this 40 kilometers per hour, which is really helpful because then we get rid of all that excessive noise at the end. Then all the variables that you care about are starting from rest, max velocity, this R here, which is the radius of the track, and then S, which is the distance traveled, not in linear XY, but it's curved. So that's the max distance traveled, and that is 60 meters. After that 60 meters, we really don't care what happens to this runner. I mean, maybe in another problem, but for what we're looking for here, we don't care. To analyze this problem, I've kind of already briefly stated it here. We're going to be using a dynamic coordinate system that changes with the change in velocity. And what that looks like is if you were to have a velocity here, your acceleration that you care about will be parallel to the velocity, and then you'll also have another acceleration that will be perpendicular to that velocity. And this is the tangential acceleration, also known as AT, and this is the normal acceleration, also known as AN. And the reason that this is so important for this problem is because when it asks for the max acceleration, if you were to look at the classic X and Y, it would be hard to define based on what we're given at which point in time there would be a maximum acceleration. Because if you were to look at the maximum acceleration here, which is the maximum velocity, you would have to take into account the positive and negative components. So you can do it, but it's a little bit more complicated. Whereas this, easy, maximum change in speed, maximum change in direction, is going to be the point where the person's moving the fastest. And another thing I want to point out about the problem statement is it gives that's a horizontal acceleration. It's not horizontal in terms of this perspective. If it was an X and Y, they're not running straight all the way across. It can be tempting to think, oh, if it's horizontal, then it's going to be along this line. It means horizontal from the Z perspective. If you're looking at the person, they're not running up a hill and they're not running down a hill. If that was to occur, there would be an additional component of acceleration that we would need to take into consideration. But thankfully, they simplified it for a little bit and say that they're running on a flat surface, so there's only acceleration in the horizontal plane. Okay, so because we're looking at a dynamic coordinate system, it really doesn't matter the orientation of those vectors. So if we were to say that V naught was to start here, and V final was to end here, this would be E of t, which is going parallel to the velocity at the initial position, and this would be et as well. It is changing as time changes. The S will be defined as this here, and R is this. And when you take it out of context of the track, it simplifies it in your mind a little bit, because now we're back to something that we're very comfortable with, looking at just a circle. So first we'll calculate the change in speed. And I like to distinguish between the tangential and normal acceleration by thinking about it as if it were a car. And there are the wheels. This is E tangential, and we'll say that this is E normal. If we're looking at just the change in speed, which is the 40 kilometers per hour, that would be as if we're seeing the effect that the gas pedal would have. It's not a change in direction. If you got in a car that all the wheels were for some reason fixed and you were to push on the gas pedal, it's just the speed that changes. Where the changing in the position of the wheels, if the front wheels were to turn, that would be changing the normal. So we're just going to look at the speed. And if we're just looking at the speed, then the direction of it doesn't matter. So let's take this and roll it out flat to where instead of being a curve, it's actually now just a straight line. So our S naught in this case will be equal to X naught, which will be equal to 0. Then our S final will equal X final, which will equal 60 meters. And at this point, the magnitude of our person's speed is 0, and then the magnitude of their final speed will be 40 kilometers per hour. So the reason we had to look at the magnitude is because we're not taking into account the direction, just the magnitude velocity. And we've done an equation like this before where we're just calculating the change in speed. So we can use those equations, and that is going to be v of x, because that is v in terms of x, and it includes an acceleration. Because remember, we have v, we have x, and we're solving for acceleration. So v f of squared equals v naught squared minus 2a x of f minus x naught. Before, this has been gravity. It's also been the negative 0.4. And in this case, we're going to make it a tangential. So when you plug in those values, this is 40 over 3.6 to do a conversion to meters per second, 0 minus 2 AT, 60 minus 0. Solving for AT, we get 1.029 meters per second squared. And that is the change in speed. However, we've only looked at speed as a magnitude. What about direction? How do you calculate the change in direction when you're using a dynamic system? Well, obviously use AN, but I want to go through the derivation, a simplified derivation for the normal acceleration, because it's a little bit odd in how you get to it since it is a change in direction, but I find it kind of interesting, and hopefully it'll give you some context of where it's actually coming from. So, speed, done. Direction, if I could spell, I don't know. So we know that dv, acceleration is dv over dt, and that can also be the second derivative of position. And if that is if it were in this coordinate system. But if we were to change to E normal and E tangential, you get a different kind of equation. And what that looks like is the acceleration of this ds over dt squared et. And this is the speed that we just calculated. That's the acceleration that we're familiar with. It matches this a lot. But what we already discovered is that this is just the speed and it doesn't take into account direction. But if you were to have this plotted along a line, so at t1, this is the facing of et. But at t2, if your et faces this way, you now have a theta from your original et at t1. And the change in this is going to be d theta over dt. And that will calculate how much the orientation of our coordinate system changes over time. So if you were to also include that in this equation, it would be the velocity times that change in the orientation of the system. but let's write that in terms of, so the change in the orientation of the system is in terms of En. Because when you calculate the d theta over dt, that's a normalization of this En. So Et, that change in the system, you can also write as this, and then you get a new equation that may be a little bit more familiar. Et hat plus ds over dt times d theta dt times En. And this is the direction. So now we get A as a function of components in Et and En. But this is a little bit of a hassle to deal with because it's in terms of theta. In our problem, we don't have anything in terms of theta. It doesn't say, oh, well, the track is this, and they're going to change to this position. And you could go ahead and calculate all that because you do have the radius and you have all what you need there. But there's an easier way to do it because you can go ahead and substitute the value of radius here so it makes steps less later. So d theta over dt, using radius, you can convert that to ds over dt. And when you plug that in, you get an even more simplified equation because it's in terms of r instead of theta. So now we have acceleration, but it's all in terms of position and the derivation of position. And this you will probably recognize even more, because this is what you may see as 1 over r times v squared. So if we were to write it in even more simplified terms, 1 over r v squared En. And that means that when you look at the tangential component, that's just equal to acceleration. And if you were to look at the normal components, that's 1 over r v squared. And most likely in physics you've calculated this before, but now you know that it comes from d theta over dt as it changes the coordinate system over time. And another thing that happens when coordinate systems are used a lot and you break up the accelerations in this way is you drop off what's defined. So AT, that has the value, so that's great. But another way we can write what we had solved up here is A equals 1.029 times ET. And if you were just to calculate acceleration and leave off the t or leave off this, then it's not the full story of what's going on because this is not the complete acceleration. If you were to solve for 1.029 and plug that into Wolfram alpha and say that's the magnitude, you're missing the acceleration that is required for the change in direction. So don't get lazy. Make sure that you include the tangential here or include the tangential here, or else you'll get yourself confused. It's real easy when you start dropping off what you need. Okay, so we've derived the equation for the normal because we took into account this change in theta. So let's plug that in and we can finish working the problem. AN equals 1 over r v squared. And if we plugged in 1 over 39.9 meters times the 40 over 3.6 for that conversion, then we will find that A equals AN. See, I'm already doing it. Maybe that's just me who messes up. Actually, I know it's not because I've seen other people do it as well. Meters per second squared. And with this being in the n component, we can get our final acceleration as 1.029 ET plus 3.09 EN, and all of that is meters per second. And what we know with any vector that we have that is perpendicular to each other is you can use Pythagorean's theorem to solve for the magnitude. And don't forget that these triangles have to be perpendicular for you to be able to use Pythagorean's theorem. Because if they're not, then you have to use like law of cosines or law of sines. So when you solve for this, it's 3.26 meters per second squared. And that is the complete magnitude of the acceleration. It's not just this 1.029, and it's not just this 3.09. You have to take into account the change in speed and change in direction. So let me know if you have questions on this. We're starting to get into it. This is a fairly straightforward problem, but pretty soon there'll be even more tricks that you have to do to solve for it. So just let me know if you have any questions now, and hopefully that'll help you out later.